We present ARC Actor Residual Critic for Adversarial Imitation Learning. Our motivation is that the reward in adversarial imitation learning is differentiable in shape. Hence, we propose a new class of reinforcement learning algorithms to leverage this property. Adversarial imitation learning casts the imitation learning problem as a two-player adversarial game between an agent and an adversary. The agent generates trajectories and the adversary generates a reward. The adversary is trained with supervised learning to classify between agent and expert trajectories, and the agent is trained with reinforcement learning to maximize the reward, which incentivizes it to fool the adversary and imitate the expert. One interesting property in adversarial imitation learning is that the reward is differentiable. On the left-hand side, we see the general case of reinforcement learning where the reward need not be differentiable. On the right-hand side, we see the specific case of adversarial imitation learning where the reward comes from an adversary. And since the adversary is usually a neural network, it is differentiable. To leverage this differentiability property, we need to make a modification to the critic function. Standard critic or Q function approximates the return. Since the immediate reward in adversarial imitation learning is known and differentiable, we formulate a residual critic or C function which approximates only the future return. C and Q have a simple relation. Q is equal to R plus C. Standard actor critic algorithms take the gradient of the Q function to update a policy. We instead formulate a new class of RL algorithms called Actor Residual Critic or ARC. ARC is any RL algorithm that uses an actor and a residual critic. To update the policy in ARC, we take the gradient of the immediate reward and the C function separately. The advantage of this approach is that the gradient of the immediate reward is known exactly and we only need to approximate the gradient of the future return through the residual critic C function. Implementation wise, it is very easy to change actor critic to actor residual critic, which makes our method practical and appealing. With this change, we can have an ARC counterpart to any actor critic algorithm as long as the reward is differentiable. For example, from DDPG we can get ARC DDPG, and from soft actor critic we can get soft actor residual critic. We now show some of our results showing the advantage of actor residual critic. First, in a toy environment, we show that using ARC we can get more accurate gradient to update a policy as compared to standard actor critic. We test ARC on Mujoko continuous control tasks, which are ant, walker, half cheetah, and hopper. In all of these tasks, we see that ARC gets higher performance as compared to standard actor critic. We then test ARC on robotic manipulation tasks, which are simplified versions of reach and push tasks. In these tasks, we train policies in simulation and deploy them in the real world. Again, in these tasks, we see that ARC gets higher performance as compared to standard actor critic. We visualize the action magnitude coming from different methods. The black dotted curve comes from the expert, which initially executes high magnitude actions, and as it reaches closer to the goal, the action magnitude decays to 0. ARC algorithms shown in blue and red curves show a similar trend of decaying action magnitude, whereas standard actor critic algorithms shown in green and yellow curves show a nearly constant slope. Because of this, ARC algorithms are able to push an object closer to its goal location in a given number of time steps. For more detailed theoretical analysis and experimental results, please refer to the full paper. Links to our website and code are available here. Thank you.